Thank you. So I'm told that we should proceed according to the original time. So it's 40 minutes, 20 minutes to the next hour. It's probably a good time to proceed to the next session, to the next portion of talks. And we actually have 3 talks and the finalizing remarks by the chairs. So without further ado, let's proceed to the talk by Shuo Yang, who is a PhD student at Beijing Institute of Technology and currently working on actually interesting vision and language transformers and as I understand, the cross-modal information flow in the vision and language. So Joe, please share the screen and you can start.
Yeah, to the screen share now.
It's all good. We can see the slides. Thank you.
Okay. Hello, everyone. I'm glad here to share our EDUCATE 2022 paper, Entity-Aware and Motion-Aware Transformer for the Language-Driven Action Localization. This work was done in Beijing Institute of Technology under the supervision of Professor Wu. Now,
Yeah, thank you. This is much better. That's a better microphone.
Professor Wu. The language-driven action localization aims to localize the target moment in the video according to the given language. It is a challenging task since it involves not only the visual linguistic matching, but also the action boundary prediction. Unlike the usual action detection task that focus on the 13 classes actions, the language described actions are more specific and complex. As we all know, the action mainly consists of entities and motions. The entities are objects that the action involves, and the motions describe the state changes of these objects. While the large amount of objects, motions, and their combinations make it very difficult to handle them in a single path of the neural network. In this paper, we split the language query text into 2 parts, the entity query and the motion query, and use 2 different transformers to deal with the entities and the motion changes, respectively. Like the samples, when we want to find a person is watching the mirror in the video, we split these two parts. The first part is the entities. It may processing the persons under the mirrors. We first find where persons and mirrors are present in the video, and then in their appearance, we can then find the motions where it's watching happens. Then in the short durations of the video, we can very quickly find the boundaries of the actions. Well, the objects in the visual images are more salient and can be matched with the nouns of language using the visual appearance of the image without considering the complex temporal motions. Thus, the object can be easier modeled by the feature of the single frame and can be enhanced when using the complementary of the information of other frames. So it can be easier determined whether the object exists in the current frame. And we can get cross-temporal action candidate according to the object in the long read video. Well, the action boundaries are usually determined by the motion changes described by the verb of the language. To accurately estimate the action boundaries, we must carefully model the motion changes considering several frames or even the whole video. It is challenging to capture these changes in untrimmed video since the long videos contain the various content. Thus, we estimate the target actions in a short temporal regions that are related to the objects, and we neglect the objects that not showing in the video. That we can hugely narrow down the searching space and can focus on the motion changes. In this work, we focus on the motion changes both the globally and the locally. Next, I will introduce our method in detail. Our method consists of 3 parts: the entity and the motion query extraction module, the top and the down part in the figure, entity-aware transformer, and the motion-aware transformer module. The entity and motion query extraction module encodes the input image query into an entity query and a motion query via the standard transformer under the guidance of the part of speech tagging. The entity-aware transformer incorporates the entity queries into the visual features via the cross-model and cross-frame attention to predict a per frame entity relevant score, which can be used as a soft weight to each frame being a desired action. And the motion-aware transformer captures the global and fine-grained motion changes at a multiple temporal scale via the STM transformer. Both the entity-aware transformer and the motion-aware transformer, we use a context query attention as the cross-model fusion. Overall, starting with the more accessible entity, the entity-aware transformer closely locates temporal regions where the desired action is more likely to happen. And considering the global and fine-grained motion changes, the motion-aware transformer localizes the exact boundary of the desired actions. Next, I will introduce each component of the framework. First, for the entity and motion query extraction, we get a input language. We split it into entity query and motion queries. We first tag each word by the part of speech functions in natural language toolkits and group all the words into three groups. The non-related groups, which are most non-related, and the verb-related groups, and other groups. Note that we group the adjective word into the non-related group and the adverb word into the verb-related groups. And we keep the other group words unchanged. That's example is that a person is watching the mirror. We will get an entity query. A person starts the mirror, which is the non-word person and mirror, and the other word like the and the other meaningless words. Motion queries can be get in the same way. For the cross-model fusion, we use the popular context query attention in LP to learn the word frame level interaction. First, we compute a similarity between the word, every word and every frame. And it followed by a softmax normalization, both for rows and columns. And then we get two attention weights between the frame and the word. And we use the attention weight to filter out the query-related visual features. And finally, we concat the original visual features and the query-filtered visual features. In this way, we get a query-related visual feature. And there are two types of transformer in our method. The standard transformer blocks, which are used both in the query extraction module and our entity-aware transformer module. In the standard transformer block, the self-attention unit uses a linear QKV function, which is a unimodel that only considers the current frame. And we say that they concentrate on the content of frame. So it is suitable for our entity modeling. And in our visual motion-aware transformer module, we use a LSTM transformer to capture the global and local motion changes. The LSTM transformer replaces the linear functions of QKV to a multiple temporal scale LSTM, so that it can take considering the neighbor frames to capture consistently motion changes and their interactions. In this way, the standard transformer attends complementary information of objects, and the LSTM transformer focuses on the motion changes information. We then use for the LSTM transformer, we use a multiple temporal scale LSTM, since the action pace in the video is not always the same. For one hand, different people do the same action in a different pace. For another hand, the sampling strategy for video processing leads to the different duration of the same actions. So we use a multiple scale LSTM transformer to capture the different temporal scale motion changes. The parameters in the same scale are shared, and the result from different scales are concatenated. Finally, there has a prediction module, and we have two types of prediction. A per frame prediction, which predicts a probability of each frame being an action foreground. And this prediction focuses on the content of the frame, useful for the cross-model semantic matching, and a start-end point prediction, which predicts a probability over all frames, which being a start or end of the action. This prediction focuses on the relation of the frames, useful for the action boundary localization. For the experiment, we evaluate our method on two popular datasets, the Sherry's STA and the Tacos dataset. The Sherry's STA dataset is an indoor activity performing by different persons, like the 10 rat open doors, and you seeing a person watching mirror and other things. Well, the Tacos dataset is a kitchen activities. That are two different datasets. The Sherry's STA dataset usually do the short videos, only contains minutes of videos, while the tacos dataset have a silver long duration of the activity. And the metric used is the recall at K. Here we use the recall at the top 1 and the LU equals to the mu. The LU is the temporal overlap of the predictor and divided by the union of the ground truth. And the mean LU is the top 1 mean LU over all data set. In this tables, we can see our method can compete all the previous work by a large margin, which can validate the superiority for our proposed entity-aware and motion-aware transformers. And we do ablation study on the shared STA dataset. We compare our method with the baseline method called ours without EA trans. In this method, we remove the our entity-aware transformer and only use the motion-aware transformer by input all the languages. We can see a clearly performance drop when we remove the entity-aware transformer, which means our progressive localization strategy is very useful. And to demonstrate the superiority of our LSTM transformer, we replace the LSTM transformer block to a standard transformer block, like a FC trans. And we replace the multiple scale LSTM to a multiple scale T convolution. That means temporal convolution, which also can capture the local motion changes. We can see that when we use the FC trans, the huge performance drop, which means the local motion changes can be handled explicitly by our LSTM transform. And for the local motion changes, we replace the LSTM transformer to a temporal convolution and our LSTM. We don't use the whole transformer block. Here we can see when we use only the temporal convolution, nearly 10%, more than 10% performance drop, which means the global motion changes is very useful. And the LSTM transformer also has a 2-point performance drop, which I think is the LSTM transformer lost some information for the long video. And we also test the number of skew effect of our LSTM transformer. We observe that when the skew number increase, the performance can first increase and then gradually decrease, which demonstrates that the modeling local motion changes at more temporal scales can improve the location precision, localized precision, but also may bring some redundant information when we use the too large scale number. Finally, we extract our quantitative results in figure 4. From the first 3 cases, we show the entity where entity relevant scores in the bar. The brighter color indicate the high related values. We can see that our entity-aware transformer can locate the coarse regions of the target actions. And our final result is nearly overlapped with the ground truth. However, in the last cases, the entity word drink is wrongly classified to a motion word, leading to a wrongly prediction of the final boundaries. In summary, we propose a cost-to-fun framework for language-driven action localization, which progressively estimates the action boundary with high precision. And we use the entity-aware transformer to match the appearance feature of video object and the non-face of the language query. And we propose a motion-aware transformer to deal with the alignment between verbs and the motion changes of action by integrating the multiple temporal scale long short-term memory into the self-attention. That's all my presentation. Thank you.
Thank you very much for the presentation. We're a little behind the schedule, so we probably have time for just one question. Anybody has a question?
I have a question. Your pipeline for think of that. Okay.
So there is Dmitry, there is
Okay, I'm afraid we can't hear it on the Zoom.
There's one question in the chat.
Oh yeah, so the question in the chat is why don't you just use pre-trained GloVe instead of training embeddings with transformer?
Yes. In our for the language input, we use the two pre-trained models here. Here the 3D CNN features are for the visual feature pre-trained, and the GloVe embedding is also used the pre-trained for the language, which are fixed in all the framework. And our training module is included these two transformer blocks and the transformer followed by the GloVe embedding.
Thank you. A very quick yes or no question from me. So I see LSTMs and transformers on the same slide. So are LSTMs dead or not? Like the famous article was suggesting that LSTM is dead, but you are still using it. What's your opinion on that?
LSTM can because I think the motion change there for the video is constantly and sequentially. For the very detailed actions like that, we want to locate the action boundary. The constantly motion change is very useful. So which is the LSTM working procedure. So we incorporating the LSTM procedure as the basic motion changes to the transformer blocks. Like we learn the very detailed motion changes by the LSTM here, and their interactions like the global motion changes, which are performed between the detailed actions. So our LSTM transformer can capture both the local motion changes and their interactions we call the global motion change. So we can locate a very precise the action boundary.
Okay, thank you very much. And we are ready for the next speaker in our
Okay.
last session. So please, Dmitry Kamzolov, if you're online, please kindly connect. And it's a pleasure to introduce Dmitry. He's a research associate at Mohammed bin Zayed University of AI. And the talk will be about damped Newton method that achieves some impressive convergence rates. So please share the slides.
Hi, do you hear me? Do you see everything?
Yes, it's all good.
Fine.
Thank you.
Okay. Hello. Yeah. Thank you for invitation. My name is Kamzolov Dmitry, and I want to present my paper about. It's actually the talk will be about second-order information and how to use it to speed up optimization methods. So the first part will be based on our paper on damped Newton method that achieves global k-square convergence for convex problems. It's joint research with Slavomir Hanzeli, myself, Dmitry Pasechnyuk, Alexander Gasnikov, Peter Richtarik, and Martin Takac. And this paper was accepted to New Reps 2022. And this is the first part of the talk, and the second part will be about how to use second information to optimize convex and non-convex functions better and faster. So it can be applied for neural networks and other setups. So first part will be about convex problems. Let's say we have the problem minimum f of x. F of x is convex function with Lipschitz continuous gradient and Hessian with L1 and L2. So it's like this. So the gradient is smooth and Hessian is smooth. It also means that the Hessian is bounded in the operator norm and third order derivative is bounded, so like respectively. So first part will be like this part will be quite easy and well known. Let's say we have Taylor approximation. This is first order Taylor approximation, and this is second order Taylor approximation of the function. And we want to use it to optimize the function. And we can make such an upper and lower bound like this, where P it's in general 1 or 2. For example, 1 for this case and 2 for this case. It's also true for non-convex functions like this bound. And by this bound, we can get an optimizer that will optimize the model, not model like this, not the function. So we will find the solution of the problem, the minimum. So from this one, we can get this one, like just remove absolute part. So from that idea, we can get the simplest method. It's gradient method. It looks like this. It's the first order approximation. And if we calculate the step, so to calculate the step, we need to take a derivative of the inside part by h. So the derivative will look like this, and it should be equal to 0. Then the step will be equal to well-known part, like minus some constant by the gradient. And the convergence looks like this. It's all well-known. So the second order model looks like this without regularizer. And if we optimize this one, we will get take a derivative, solve this equality, and we will get the Newton step, a very well-known and classical Newton step. But the problem is that so what we know that it's the Newton step is using second order information. It's very fast, but it can diverge if the point is bad and far from the solution. That's why it was proposed damped Newton. It works, but it works slowly. In 2006, Yuri Nesterov and Boris Roshpolik, they proposed cubic regularization. So they regularize the part inside. And now this is an upper bound, because before this is a non-upper bound. So and we also can use the step to find the solution of the side of this subproblem. We can take a derivative. It will look like this. H will be look like this. But now the problem is that here we have inside a norm of H, and so H depends on the norm of H, and H is also inside of the inversion, so it will correct our like also like it will correct our steps. So it's this problem is much harder to solve because we need to use some line search to find this norm and find H. So this step is better in terms of convergence because convergence like this. But the problem is that to compute the step, we need to use some line search and multiple number of inversions. So it's expensive. And now I move to our part of our paper. The motivation was to remove, to save the convergence speed, but remove the hardness of this subproblem. To do that, we need a local norm. This is called local norm because it's in Hessian norm of current point X. And this is more natural geometrical norm because it's like all dimensions will be the same in this, like it will be a ball around this area, not the ellipsoid. So so the local gradient norm, it's dual norm for this one, but it's Hessian in power of -1, so it's inverse Hessian. And this is for gradients, and this is for points. And next we move to operator norm. It's to measure Hessians, like this. So we have to change our assumptions about functions because we don't want to fix L2 norm. We want to change our norm to local norm. And to do that, first it was proposed, I think also by Nesterov and Nemirovsky, self-concordant functions. It looks like this. So the Hessian is bounded by third power of local norm. So it's like kind of like this. And also by Nesterov and Doika, there was proposed this strongly self-concordant function if it's the version of this one, but stronger. It looks like this. And the problem here is that if you see that there is a point X, there is a point Y, and on the right side, there is point Z and W, and maybe it will be hard to find such a function for this strongly self-concordant. And in our case, we use a semi-strongly self-concordant function. And this is looks more normally because this is just operator norm. And we change, like before here it was second norm, but now it's X norm, so local norm. And LF is also different. But yeah, so from this condition, this one, the same as for the normal second norm, we can get upper and lower bound like this. And this will be our new upper bound. So from this, we can get a method that looks almost the same as before a cubic Newton. But the main difference, and I want to highlight on this, that now here is X norm, but before it was a second norm here. So we changed this norm to more natural, a local norm, and get a new method. And we can prove that the convergence will be the same, k square. But now the question is, this subproblem is easy or hard? And the answer, this subproblem is now very easy. It's almost the same as normal Newton method. If we calculate the first order, like because here it will be Hessian. If we calculate first order derivative of this part, we can just get step size alpha k like this, that depends on gradient norms and LF. And this method, like this, with alpha k like this, it will work with the same speed as cubic Newton. but the step is much easier, as you can see now, because it's just some constant. And we can also apply some adaptive schemes for this alpha. But we don't need to calculate additionally any line search for this part, and to make the step, to solve the sub-problem of the step. And next, and so if you, now we can see the convergence. It's for MNIST. The convergence is for, like, our method is red. It's IC Newton. Blue is cubic Newton, and they're almost the same. So this difference is up to the tuning of the constant L2 and LF. So if I tune cubic a little bit better, like if I tune AIC Newton a little bit better, it will be like better than Newton, cubic Newton, yes. But so the main idea here is that their speed is almost the same, but if you use just damped Newton with fixed step size, it will be much worse. You can see here that just damped Newton is much worse. So we show that if we choose the step size for damped Newton smartly, in our case, we can get the same convergence as cubic Newton. It's like a cubic Newton, it's like the main method of this main second order method now. Like state-of-the-art method, kind of. And yeah, and this is also like one of the new method, global regularized Newton by Konstantin Mishenko. So now we can move to kind of motivation of why we want to explore second order methods, and why it's interesting. First, let's say we don't know exactly Hessian because it's expensive to compute the Hessian. We know only BK, where BK is an exact version of the Hessian. So this is variant of inexact cubic regularized. Exact cubic regularization, whereas BK here. But I think we can apply also BK for our method in different norm, so the problem will be easier. This is version of an exactness, but you can think on an exactness as like how close matrix BK to the Hessian in terms of SVD and like biggest eigenvalues and smallest eigenvalues. Normally, we care about largest eigenvalue more. So this will be delta, and the convergence will be like this. So you can see that even if BK is 0, and delta in the worst case scenario, if BK is 0, delta will be just L1 because it's an upper bound of Hessian. It will be still not worse than gradient descent. So if we not introduce first order information at all, will be the same as gradient descent. But if we introduce some information, we will get improvement because delta will be smaller and this part will dominate left part. So what are the examples of inexact Hessian? The first, and this was very simple, it's L1 multiplied by identity matrix, and in such a case we get a gradient method. Second, it's called diagonal preconditioning. We can compute diagonal of the Hessian. In practice, it's impossible because it's as hard as compute Hessian in general, but at least we don't need the inverse Hessian. We'll just use its diagonal and inverse diagonal matrix, so it's fast. But in general, like it's only theoretical case, but we can somehow approximate diagonal much easier compared to the full Hessian. The very well-known non-convex method ADAGRAD is, from one perspective, it's adaptive learning rate for SGD, but from the other perspective, it's also some adaptive approximation of the Hessian to get better second order information, and it's well known in non-convex optimizers scene. Hermes prop is also well known non-convex method, and it also has some approximation of the second order information. Next, we move to diagonal preconditioning. For this case, an exact version of this diagonal preconditioning was presented by in this paper. It's called OASIS. So here we're using such an effect that if we have random vector zk and we calculate the Hessian vector product, this Hessian vector product is as simple as to calculate the gradient. So it's kind of simple to calculate Hessian vector product. Then we coordinate-wise multiply it with the same vector, and such a procedure will approximate our diagonal of the Hessian. And we have a paper on arXiv now, like this one, where we use this preconditioning to use it with Sarah and as LSVRG. These are variance reduction methods. So it's the same preconditioning in this one. And you can see here that let's move to the next slide. Sorry. This is non-convex problem, and Adam is also using second order information because it's the version of Adagrad but with momentum. So we can use here that we can see here that just stochastic methods, they are like their convergence can be accelerated by using preconditioning, because like this the full line, it's general setup, and so like this is without preconditioning, and these lines, they are with Hutchinson preconditioning. So, and they are much faster than the originals, and also they are faster than Adam. And Adam is already with preconditioning, so but with Adagrad type of preconditioning. And this is different data sets on here. They are very more close. It's a function value, it's a norm. So here in norm is, I think, the best to show. So here is also, you can see that norm is much smaller for Hutchinson preconditioning, and here also. And for error preconditioning are much better than regular methods. So because of that, it's interesting to explore how we can find better preconditioning, better using second order information, but without expense of second order information. So this is like one of the research direction of our group. So I think that's all. To summarize, so it is interesting to find out what is the better, how much information we can extract from Hessian, for example, by Hessian vector products, and use it to accelerate optimization methods to find these problems, like find a solution of non-convex problems much faster and much better solutions. Yeah, this is my context. If you want to like ask something, you can. But yeah, I think that's all. Thank you very much.
Thank you very much for the presentation. Are there any questions?
Hello. I have a question. Many thanks for your interesting sharing. My question is, how about the time consumption comparison with its existing methods?
Like
About
comparison in
the
terms of
time
time?
consumption.
So in general, you can see that. So if you compare for first part, if you're comparing, all of these methods are second order, so they have the hardest part of them is inversion of the Hessian, but also like for cubic Newton, you need to calculate SVD because because line search without SVD will be too expensive. So for example, for our method, we just enough to compute one inversion. For blue, you have to compute SVD, and SVD normally is much more expensive to compute. And for these cases, I think in general, the time consumption is almost the same as just SGD, because you just use already known information in undergrad Remus probe. Here you use Hessian vector product. It's like twice to calculate the gradient, so it's some small constant. It's almost the same as also like undergrad and other stuff. So it's cheap, and we calculate this one only once per iteration, so it's also cheap. That's why this is, so we get some good approximation of Hessian and use it to accelerate our method. And it's applicable, like, also like the main part of this paper is that preconditioning applicable to almost every method, and almost every method can be accelerated by preconditioning because you just insert this information inside of the method, even if it's variance reduction, non-convex, convex, just you use second order information and it can accelerate your method a lot.
Okay, I see. Interesting work. Thank you.
Thank you.
Do we have other questions? So, Dmitry, you guarantee both local and global convergence by this method. Am I right?
For convex, yes.
For convex case.
Yeah.
And if it's really bad non-convex case, can you compare it to this cubic?
Like Newton? Cubic also is well known for non-convex, and like our method will, for example, if it's star convex function, it's non-convex, but star convex, it's like cubic is still working, and our method is also will be still working, I think. Like as it is not in our paper, but as I can say, it should be working the same. And for but I don't know about this part. If this is true, so it will be working. And for non-convex, I think second order methods, they are showing like you don't need to, how to say it, you don't need to compute full Hessian, because that part is normally only from theoretical perspective. But after that, you can somehow approximate this Hessian, and you will get first order method, but with second order information. And from my experience, for example, if you have some small neural network, Adam will never learn it good enough. But like some Newton plus CG, like trust region methods, cubic Newton plus CG or something like this, they will learn it pretty good, even if it's non-convex.
Thank you.
Thank you.
Okay, I guess we need to return to our regular schedule. So thank you for the talk. And our next speaker is Mikhail Burtsev. So Mikhail Burtsev is a scientific director at AIRI, and also a lot of us know him as a developer of the Deep Pavlov. And but today the talk is about long-term memory, as I understand, and the memory in neural networks in general. That's probably the 2022 paper at NIPS if I am correct. So Mikhail, please start. Thank you.
Yes, thank you a lot for inviting me for this workshop. And I will try to move fast from my presentation due to our slightly delay of schedule. So why memory for neural networks are important? First of all, we can consider memory as some kind of workspace where we can jointly represent some current context which is feed to the input of the neural network, as
Mish,
well as some.
So we don't see.
Yeah, I don't. Do we have slides or not yet?
Yeah. Sorry.
Without slides, you're talking quite good, but.
No, I just forgot that I need to share them.
We have very long-term memory. We remember everything.
Yeah. Because I decided that I need to rush into the presentation as quick as I can. So I forgot.
It's all good now. Thank you.
Okay, thank you. Sorry for that. So, okay, my presentation is about how, some general method how we can add memory to any recurrent memory, recurrent neural network architecture, and why memory is important. Because I think that we can consider memory as some kind of a workspace in our model, and this workspace can allow us to represent jointly current context, which is like current input of our neural network, with some important historical information which are required also to make correct decision or correct prediction. So it's something like workspace where it can be combined. And also memory is not only workspace, but also some storage for intermediate results of calculations, or some storage of the previous signals from our sequence or from other sources of information. So this work was motivated by reinforcement learning settings. And the idea was what is happening when we have some signal at the beginning. Here we have problem of T-maze in reinforcement learning, where you have starting position and then you have states, and depending on the hint on the signal at the beginning of your sequence, you should select correct decision at the end of the corridor. You should turn and go left or to go right. And this is a very simple toy problem that can be adapted to simulate and to study problems which requires long-term memory, because you can easily extend this length of this arm to be much longer, and to test all different approaches. So what is happening? So here we have some, like, what is the major features of this problem? So at the beginning we have some signal, then we need to transition many states, and then we, at some point at the intersection, we need to use this memory or information about this signal to make a decision. And if we have no this memory, then we cannot predict what is the correct one. And this is a toy problem, but on the other hand, it's a problem which can be encountered in many other domains. For example, if we consider natural language processing, when we process long documents, for example, we have a long paper, and we have some, at the beginning, we have description of some method, some experimental method, and at the end we have conclusions, then, or some presentation of some results. We need to have information about methods to understand if the conclusions are right or wrong, because this method, it's like a condition for interpretation of our results. And certainly, if we consider current approaches, so majorly till last years, we have used LSTMs for solving these long sequence problems. But usually we have like maybe a few hundred of, to calculate LSTM, you need to use backpropagation through time, and usually you truncate gradients at some depth of unrolling of your backpropagation through time. And usually in recurrent architectures based on LSTM, you have unrolling for maybe a few hundred steps, not thousands and so on. So, and this limits applicability of your method, because you can learn only dependencies which lies inside this unrolling of the backpropagation through time. So here in our example, if this important signal denoted by red is much earlier than, so let's say that we unroll on 500 time steps in the past, but our signal lies like 1000 steps at the past. So our backpropagation cannot learn these dependence by default. So it cannot learn that this signal can be used to predict this future at this blue state. So and we cannot extend this because we will encounter instabilities, and we have limits on our memory. The same is with the transformers. So we're trying to increase the size of the transformer input, but in the classic transformer architecture, we are limited by a quadratic scaling of memory and calculations. There are some approaches which allows you to make it sparser and then get rid of this quadratic complexity. But still, even if we take like the most advanced architectures, they are like maybe a few thousands of the length of the input sequence is about a few thousands. So still, if we cannot feed to the input of into the input of transformer our signal, important signal, and our decision point, we cannot learn that. So can we scale our learning to longer sequences? And we think that we can. And we propose to use such heuristic. So we say, let's first, if we already have some initial model, and we can estimate uncertainty of prediction for some elements of our sequence, so we can use this information to train our network to remember and to use signals from our from some signals in our sequence, which are important for reducing the uncertainty of these specific elements for these specific predictions. Which means that if we have, if our model is unable to use local information to predict some specific future event, but maybe some non-local, like from the deep, some information from deep past can be used to resolve this uncertainty. We can try to train memory to retain, first to extract this information and then retain it until it is required for making prediction. So let me show it on this like diagram. So we have our very long document, and we can denote different elements of our sequences with these circles, and we can split them on 3 different types. So here we have our model, and these red dotted rectangle shows like local context which can be fed into the model at once. And so let's look at what type of elements we consider in our approach. So first type of elements is the elements which can be easily predicted by our model given the local information. So these black circles, these are elements which can be predicted only considering other elements which are inside this rectangle. So you can train your model like in traditional way to predict them. But there are some other elements like these yellow ones which can not be predicted only with information inside this red rectangle. Because of course, certainly, maybe these elements cannot be predicted from the ground, so maybe they are truly random. But some of these elements, they cannot be predicted with local information, but maybe, for example, this element depends on the state of this red element. But these dependence cannot be learned because this red element cannot be fed into the model together with this yellow element. So what we propose to do, we are saying that we have these red elements which consider some important information. And at the beginning, we have no idea what are these elements, and we need to build a system which will allow us to find these red elements. For example, if we have these yellow element, which should be predicted somewhere far into the future, and but information which is important for prediction state of this element contained in the value of this red element. So you need to retain it for many steps and then use it to predict the state of this yellow element. We propose the method how to train a model to find these red elements and to store information about their state during the movement of our model along this sequence. So how we propose to do this? Say you have already pre-trained model, local model for our sequence. So then you can use this model to calculate uncertainty of prediction for every element given local information. Then you can tag or annotate elements of your sequence with this uncertainty. Then you select some top k most uncertain elements from your sequence. And then you go to other step. You say that we extend our model with some recurrent memory. And also we have some auxiliary model, which we call predictor. And we train these three parts together end to end to predict not only the next, say, if it's like the next element prediction into the sequence, we train our model not only predict the next element into the sequence, but also predict the state of these future elements given the current input. And in this way, we creating like a new flow of gradient from these future states through this predictor memory and model to our current to the current input of the model. So it can be trained to first to find elements which are important for predicting elements into the future, and then as we use recurrent architecture and we go step by step moving along this sequence, it is also then the memory is trained to store this information and retain it until decision is made. So this is like the basics of our method. And it should be noted that it can be combined with any neural architecture recurrent neural architecture you can imagine. And it requires only like 1 or 2 steps unroll compared to other recurrent architectures. So here are results of application of our method. And it's results for this toy problem with T-maze, where you have like 100 and 1000 size of these long arm. And you can see here that LSTM or AMRL, it's another memory-based method. They cannot solve this problem if they cannot see the whole corridor, the whole state. But our method, even with unrolling only 1 step backward for recurrent architecture, can solve this problem easily. So the first 1 million step, it's pre-training of this memory. And after that, we use this memory to train our agent to solve this problem. Then we also test this on this zoom to color problem, when you need to store in memory color of the column at the beginning of your trial, when you placed in the environment, and depending on this color, you should collect either red or green armors to succeed. But also this method can be applied beyond reinforcement learning setting, also to supervised setting. So we applied it to a number of benchmarks for long sequence processing, like copy tasks, scattered copy, permuted missed classification, and addition. And we compared it with LSTM, sRNN, and transformer, as well as with truncated versions of these models. So because in our case, we have like only 10% of the sequence which were used to unroll backpropagation through time for our method. And we use the LSTM model as a backbone here in our experiments. So we compare with, for example, with LSTM, with truncated LSTM, which is also has only 100 steps for unrolling, or with the full LSTM, which can see the full 1000 steps of the sequence. And you can see here that surprisingly, this method performs on par with the other methods, which has full information about the sequence. So again, our map here, it's a bold red line, can see only 10% of the sequence, like only 100 steps. But it has the same accuracy as transformer, which can see the whole sequence at once. So this means that the transformer has full information about the sequence, not only partial ones. And we were impressed that this method, even if it's used much less memory, and can see only local information, still able to perform on par or with transformer here. And you can see it beats all other recurrent methods, even if these methods can see the whole sequence. Here, for example, LSTM, if it can see the whole sequence, still performs worse than our method, which can see only part of it. So, okay, let's switch to conclusions. So we proposed a new method for training long-term memory in recurrent networks, and the experimental results show that it allows to learn temporal dependencies which are significantly longer than length of backpropagation unroll for the training. And this method allows dramatically reduced memory consumption Or on the other hand, if you use the same memory, it can increase the length of processed sequence. And it can be applied to supervised as well as to reinforcement learning settings. And as we've seen from results, that even in recurrent mode with truncated backpropagation through time, our approach, which is called MEMAP, performs on par with the methods which has full information about the sequence. So thank you for your attention.
Thank you very much for the presentation. Are there any questions in the audience or in the Zoom? I will go with the first question then. I'm sorry, Jin Chen, did you want to go ahead? Okay, so I'll go ahead then. Basically, I want to understand your word choice, because you called explain my surprise, and it really looks like a deja vu when you basically saw something long time ago. It's not a surprise, it's like something that you've seen. Can you please elaborate on this word choice?
So the idea is that we have these highly surprising events which we cannot predict given our local knowledge, and we add memory which allows us to explain these surprising events.
And isn't this setting when you basically have high uncertainty, and then you, especially when you edit annotation, you said, is this similar to the active learning in any way? Maybe you can differentiate it? Mm-hmm.
Yeah, in some sense, it is similar to active learning, but active learning, it is like we bias our training, or we sample new important samples into our training data. But here we sample these training data from our data set and train model to remember that these elements, what is important to solve these elements, because in active learning you already have this information which you need to predict these uncertain elements, but here you cannot predict them given only local information.
Thank you. All right. I assume there are no other questions. I don't see questions in the chat. So thank you very much to all the speakers. And I'm happy to pass the word to the general chairs of this workshop. Okay. Ivan or, yeah.
Yeah, so I will start. And thank to all the speakers of the workshop, and well, thanks to our Chinese colleague who stayed until late evening. Okay, and there were a lot of really high-level talks and topics, and I hope we will be able to continue exchanging ideas and also introduce some joint research programs. I don't know, whatever type of collaboration we're looking into, including Skoltech and maybe including, well, also IRI, where Mikhail Burtsov is from, which is another artificial intelligence research institute. So I'm pretty happy that we did it, and also like to say thanks to Anastasia from our side, and can you remind the name? And Qin Hao Wu, sorry, for organizing this, because actually putting this all together in a very short time and putting the program, the abstracts, and it all worked, I think, perfectly. So yeah, thank you all for coming, and we had really a huge participation. So more, I think, almost, well, at some point even more than 80 participants. So it's a good start. So hope we will see each other in person in, well, in a reasonable future.
Okay, thank you, Professor Ivan. Next, Professor Jia will give closing remarks.
Okay, Okay, I have the same feeling with Ivan. I do agree with the feeling with Ivan, the opinion and the comments. So we spend a day of academic exchange, a day that inspired us to think. Here, I would like to express my special thanks to the 12 invited speakers to share their wonderful presentations with us. I also express special thanks to fourth session chair, Dr. Pei Mingtao, Dr. Alestra, Dr. Wu Xinxiao, and Dr. Dmitry Darlov. Once again, I'm very grateful to Professor Ivan Oslides, Professor Wu Xinxiao, Miss Anna Anastasia, Mr. Sheng Ruopeng. In Shenzhen, we have spring in the summer here all years round, and we sincerely invite friends in Russia and friends in Beijing to come to Shenzhen. Shenzhen is the largest innovative city in China, and you are welcome to visit, lecture, and vacation. Finally, I wish our friend good health, happiness, and good luck. Thank you, and bye-bye.
Thank you.
Thank you.
Bye.
Have a good day. Oh, thanks.
Okay.